sick, so he's gonna postpone his presentation.
Oh, that sucks,
Um,
man.
and yeah, my thing's not gonna be super long. There could be some conversation on it.
Cool.
We're also talking about like changing up this Wednesday thing to be shorter in general. Um, so I don't know if you have thoughts on that.
Yeah, I'm open to that for sure. What last ones went pretty late, but I guess I was presenting, so I didn't mind. Um,
JB.
but it always helps to be respectful of people's time.
Hey,
Nuts outside.
what's going on near you?
One of my street is closed, like one of those. It's one of the NYC open streets. So all the restaurants have moved their tables into the middle of the street, and it just gets a little rowdy.
It's gotta be nice.
Wait, Matt, I didn't get to check the
Tom, there's
email
a feedback
today.
loop.
What are you presenting?
Yeah?
Hold on, Tom. There's a feedback loop on your phone. I'm hearing our conversation from 5 minutes ago.
Oh, really?
Yeah, I think that's you.
Weird.
Oh no, where is that? Oh, never mind. I have the
Oh.
YouTube video.
Oh, the YouTube video. Okay, good.
My bad.
That's okay.
Evan, you asked me what I'm presenting on. I'm doing like a dynamic programming from the ground up. It's come up a few times already, and I feel like we go over like a lot of solutions, but we never talk about it like from the fundamentals. So I took the time to like write out a few documents on that, and we'll talk through them. I don't know how long that's gonna last, but it shouldn't be too long.
Cool. Yeah, I had Mustafa asking me about general testing, and then what kind of tests people run and stuff. And I've been wanting to dive into like testing a little bit more. So maybe I could.
What is your Python testing framework of choice?
I mean,
Flask.
I don't know. Most senior engineers I've met just use like PyTest and Tox.
PyTest. What's Tox?
Tox creates 3 virtual environments, like clean installs, and then runs PyTest in each one of them to make sure it's reproducible. It like just automates that.
Tokenizer?
Oh no, TOX.
TOX Python.
TOX.
It should be like a readthedocs.io website.
So you can create like multiple versions of Python, or dev versus pro?
No, it's not even that. It literally like you just type tox in your terminal. It's like almost as if you create 3 separate virtual environments yourself of your like requirements.txt, your Python version. All it does is do that 3 times and run PyTest on each one of those to make sure that if you were to clean install this on a brand new machine, it would still work as expected.
Oh my God, Aris is in YouTube watching us, and he said he lost his laptop. Oh my God.
Oh, what? That sucks.
Oh yeah. He's like, following from YouTube today, lost my laptop.
I forget that we are live streaming sometimes.
Yeah, so be careful what you say. Don't be like Lee.
I hate Python. Blah, blah, blah. Python did this. Python did that.
Where's Edwin?
I might take a break. He's literally presented for the past 4 or 5 weeks in a row. So if I was him, I would probably want a day off.
Oh man.
Okay, but I'll get started and talk a little bit about high level stuff. I know there's 4 of us and Adi's on YouTube, so there's not quite all of us, but I should kind of talk about it anyway. So I got feedback over the last few weeks. We had like a big conversation of what are we trying to accomplish here was a big one, and then kind of what are we kind of doing to accomplish those goals. And so I talked to quite a few people about what the purpose of this is, and I kind of realized that I had like a somewhat simple goal in my mind, and it's simply that I realized that if you want to teach, there's so much infrastructure around teaching that you need before you're actually able to do it. And after teaching at Columbia, like I wanted to continue this, but I wanted to doing it on my own, but I still wanted that infrastructure. And so, sort of like, I don't want to be the one running this. I actually want to be the one using this. I want to use this platform to be able to like hop in, do a lecture or present on something, or have a space where I can be like, hey guys, I'm going to go live and I'm going to code on my own project if anyone wants to join. And so that's kind of the goal that I've in my mind been working towards. Like, how do you make it very easy for people to teach so that I can be that person to teach, right? And it's selfish, but I think it's also good to be selfish in this place. In the case of like having a clearly identified goal to kind of work towards. So that in my mind is the goal. Like how can you make it as simple and as easy for someone to take the time out of their day to teach a given topic, teach a presentation or the code publicly. Then I've been kind of in the talks of trying to figure out what the structure around that should be. And so I think that these Wednesday meetings are very good for having high-level discussions and for a lot of the senior engineers who like to talk about things on a very high level, because we understand the low-level implementations and we can kind of just take a step back and be like, oh, okay, this is a good pattern, this is not a good pattern. I think we haven't been reaching as many junior people. And I think part of that is the content that's been presented has always generally been on the higher end of things, but it's also that so it's generally what the content is. So what Tom and I have been talking about is introducing this idea of doing more in-depth coding driven things that take up more time. And as such, they're probably not going to be on Thursdays, they'll probably be on a weekend. And they'll be like live coding. And so Tom and I kind of did one of those last Saturday to kind of demo it, to work out the kinks ourselves. This Sunday, I'm going to be doing the same thing. I'm going to be opening it up to kind of everyone. What I have in mind is I am working on a front-end project where I've gotten to the point where I can do a refactor that I think is a valuable refactor. And in doing that, I can kind of explain a lot of the high-level things of why I'm thinking about things certain ways, but also you get to see how this code is actually changing over time. And so those are kind of going to be the things that are more targeted towards junior people. So that's something we're going to start pushing towards, is like Saturday events or generally making this a friendly place where you can kind of hop on and be like, hey, I'm going to be coding for these couple of hours if anyone wants to join me and tag along. If you can help out, that's great. If you can't help out and you just want to ask questions, also great. So that's the type of environment that we're looking to introduce next. Then there's kind of this idea that we're pulling back the time commitment on Wednesdays. So some people have mentioned that at times it can feel like it drags on. At times it actually flies by. And I've also felt that, and I think that since we've also been having trouble kind of getting enough content week to week, that if we kind of scaled back the time commitment on Wednesdays to about an hour, and just keeping it sort of the same, where it's like an updates session, and then on top of that, having somewhat of a presentation that ultimately leads to a discussion, is a good format, but we don't need as much time dedicated to it. So those are kind of the two high-level thoughts and where we're taking things and changing things. If anyone has any thoughts right now, feel free to mention them.
Matt, this is Jotin. Love it. Absolutely love it. I think that makes a lot more sense. An hour, maybe hour 15 tops on Wednesday, maybe hour 30. That's it, and that's awesome. And then that Saturday, Sunday, whatever you've got as planned, I think that sounds really like a good idea. One request I would have is like, the projects that you pick, to work on or whatever you're going to be doing, like on the weekend. If you give maybe a week and a half worth of advance notice and any prerequisites, like let's say if you're doing some form of cross-validation, let's say of, time series model or something, right? And you just want to focus really on that. If you just give us a heads as we read a little bit about that, prior to getting on the call, I think that would just help make the session a little bit more interactive. Again, time permitting, right?
Yeah, and I think that's general advice that's good across the board, right? The more information we're able to give that people can do in their own free time, the less likely someone's going to be unable to catch up if they're so interested, right? And yeah, definitely important to know. Yeah. Awesome.
Hey, Jatin, welcome. I didn't know it was you.
I mean, congratulations on that Facebook interview. Really excited, happy for you.
Oh, thank you. But it was like a shit show, but it's okay.
It's all good, buddy. It's all good.
I know, it's just experience, man. But it was a good experience. I mean, now I have something to tell people.
Yeah. So Matt and Dom, are you going to be talking about the dynamic program right now? There's somebody, Harman Singh, or someone that you'd invited for a talk earlier.
Yeah.
Yeah.
Yeah. Go ahead, man. Sorry. Go ahead.
Harman can't make it today.
Oh, perfect.
Yeah, so it's just going to be the dynamic programming.
Awesome.
So we are going to cut it a bit short, and then yeah. So that answer your question? Yeah. Awesome.
And feel better, Herman. Hope it's...
He'll be back. Yeah, he wants to do something on Terraform, which is like a DevOps tool that's super powerful, but I don't even understand it. So definitely outside of a lot of our comfort zones. But I think that's great. Like, I think there's like, we have enough diversity in even the senior people that I think most senior people will come here and still be able to listen to something new. Cool. All right. Let's do. I will copy and paste this into a message in the text channel. I haven't published any of these documents yet. Eventually I will, but since I haven't, I'm just gonna push it as a message in the text channel if anyone wants to follow up. Okay, so what is dynamic programming? Dynamic programming is really about a certain set of problems that you can deal with. These are essentially optimization problems where you have a set of constraints on a system, and then you're trying to optimize across those constraints. I'm going to go into a little bit of detail on that, but essentially, like, if you're trying to deal with how much can you fit in a suitcase, right? That is a constraint, right? You have items and you have a suitcase, right? Your suitcase is physically constraining the number of items you can fit into it, and then you have items that you actually get value of from putting inside those suitcases, right? So the question is, can I put it in to maximize that? And so the way I like to think about dynamic programming is that it really is about trying to reframe the problem in what I call the appropriate way, but it's often just like an efficient way or an effective way for defining the problem, so that you don't have to explore every single possible scenario. You have to explore the most relevant scenarios, and you have some sort of guarantee that the scenarios you're skipping over are scenarios that you don't want to deal with. Right? The term dynamic in dynamic programming, what I feel like it refers to, and I don't actually have a source of origin on this, is that the dynamic means that it dynamically figures out which path to go down when it's looking for a solution. And I hope that becomes a little bit more clear as I go through this. But I think this is, again, one of those things that's like not as well defined as it could be, or not as well named as it could be, but I also don't have a bigger name for it. And we talked about that a little bit when we were talking about serverless. How serverless is probably better called the cloud functions, which is Google's name for it. With dynamic programming, I think there's probably a better name out there, but I haven't known it.
Man, I have a question.
Sure.
What, dynamic programming is not that the small increments that you taught me to do, like on Saturday?
No, that's better described as test-driven development.
Oh, okay.
Yeah, so when Tom and I were programming, one of the things I mentioned is that when you want to program, is you want to make small changes into your code base so that you're not changing a bunch of things, and when you change a bunch of things and something goes wrong, there's a bunch of places you have to look. Whereas if you make small changes and you test your code repeatedly, as soon as you make a small change and it goes wrong, you immediately know, and so you have a small place to debug it. There's a paradigm called test-driven development that takes that paradigm kind of to the extreme, and says basically every time you do something, you should write a test before you do it, and then your solution should just solve that test. And so if you're interested in that, test-driven development is probably the best thing to read up. But the general paradigm is to do things incrementally and to test things. That's just like a good engineering paradigm in general. Right? You want to test things as frequently. It's a good scientific paradigm too, right? You want to be hypothesis-driven. So you want to create a hypothesis in your head, and then you want to try and see if that hypothesis works.
Right.
And that's true for coding. Right? You want to come up with a guess what's going to happen to your code if you run it, and test that it works when you do run it. So that's what that means to say.
All right.
Okay, so these set of problems that dynamic program deals with have multiple solutions. Let's describe the problems a little bit more, because I feel like I touched on this a little bit. The dynamic programming problems are usually dealing with sets, and generally trying to pick a set that optimizes some other equation, right? And so when we talk about the brute force solution, that is essentially the solution that tries all possible sets and figures out what the corresponding value is, and then tries to be like, okay, we want to take the minimum or the maximum of this. Let's do that, right? So if you're trying to figure out what is the most amount of pounds that you can put in your backpack, right? You're basically saying, let's try putting everything in my backpack. Let's weigh it, and whichever outcome leads to the most amount of pounds that satisfies my constraint will be my solution, right? And so oftentimes these problems will be said in such a way that this feels like a brute force solution. You want to try out all possible solutions. And the reason why these kind of problems are very popular in the program community is because the brute force solution is often intuitively the easiest to get to, but as soon as you come up with a dynamic programming solution, you see that it's a lot more effective. And there's kind of like this mental hurdle of reshaping this problem, where you realize the same problem can be approached a dozen different ways, and that really is that is computer science. Computer science is the study of these problems, how they are solved using different algorithms, and how effective these algorithms are. Another like quick and dirty solution to greedy algorithm or to this set of problems can also be greedy algorithms. Edwin's touched on this before, but what essentially a greedy algorithm is a locally optimized solution, right? So what I'm going to do is I'm going to iterate through essentially one path, and I'm just going to pick the value that is locally optimal. So the problem with greedy algorithms is that being locally optimal does not necessarily mean you're globally optimal, right? So oftentimes you want to be globally optimal, like that is what the problems table wants you to do. It wants you to maximize based on all scenarios. But what you'll get is a scenario that you've gotten to based on incremental decisions that are all locally optimal that lead to a good solution, but not an incredible solution. The benefit of this is that you'll often get there faster, but you almost always don't get to the optimized solution, and sometimes you might not even get to a solution, right? So let's say you have a maze, right? The greedy algorithm is going to always take the step that's towards the end, towards the exit, right? And so if you have to step away from the exit, a greedy algorithm is not going to know to do that. A greedy algorithm is going to go only directly in that direction. Okay. Any questions about these two? These are kind of oftentimes the intuitive or the simple ways of thinking about these things.
Matt, sorry, I have just a quick question. So when you say, first of all, these three, so brute force, greedy algorithm, and dynamic programming, are these a subset of dynamic programming, or are these three different ways you can actually code? I didn't quite catch that.
So dynamic programming is a paradigm for just how you solve a problem.
That's right.
So dynamic programming cannot always be applied to all problems. There is a set of problems that they can be applied to. Often I think the easiest way to describe that set is the optimization problems. But I haven't thought about this from like a purely computer science mathematical standpoint. That might not be the best way to describe it. Optimization problems can be solved in any of these ways, right? You can have a brute force over that. You can have a greedy algorithm.
And just to follow up on that, your comment on that greedy algorithm, right? So you said you're looking for the optimal solution locally, but not globally. I just want to dumb it down. So, like, are you saying that if you're looking for a solution, and when you say locally, like, it's going to be limited to, let's say, the function that it's in, but not necessarily overall, like, function or method, but not necessarily applied to all the other functions, global functions? Maybe if you could give an example of when a greedy solution would be optimal would really help as a use case.
So I have a good example of about minimum travel distance, and that's a good real world example. Let's come back to that when we touch on it there, and I'll sure. For a second. Because the last thing I want to touch on is mathematical solutions, and some of these problems ultimately have mathematical solutions. They're oftentimes able to do that because they have a certain set of characteristics. Oftentimes it's linear functions, and as such you kind of end up using linear algebra. And the big thing that ends up not allowing you to do a mathematical solution is having some sort of discrete constraints, right? Discrete being that, like, so discrete math is the study of, essentially the study of sets, right? The study of, I have whole numbers only. I have 1, 2, 3, 4. And then there's continuous math, which is the entire number line. It's 0, 0.01, or whatever, all the way. And if you have continuous functions, you tend to have differentiability, and you're able to solve it through those kinds of solutions. Real world problems tend to be somewhat modeled by continuous math, but they also tend, like, you can come up with an estimate that is based on continuous math, but they're oftentimes more related to discrete math. And so if you were looking for like the ideal solution, you'll oftentimes have to use discrete math. And if that was a little bit confusing, that's because, one, it's hard to explain, two, it's hard to understand. I don't even know if my understanding is that great. But three, also, like, I think this mathematical side of computer science is very interesting, but most of the times you don't even get paid. Like, that's not why people get paid to do these. They get paid to solve problems, and if you can explain these, like the math behind a lot of these things, it's great, but it's not really the make or break things. Okay, so that's kind of the laying of the thing. One of the things I'm going to note before I go into this problem is that this is like a very good interview example question, and how I approach it, I think, is a really good way to approach interview questions. Not only that, this question is also going to be something that a lot of times, like computer science programs in algorithms courses, they'll have questions like this. And so this is kind of how I, in school, had solved these problems before. You're not solving it by writing things out. You're not solving it by writing an algorithm or writing code. You're solving it by writing an argument or writing essentially a mathematical proof using words. And so it's very interesting to come from to be in computer science, like a very action-driven discipline where you're writing a lot of code. You go into like an algorithms class where all you're doing is essentially talking about things. But that's also where interview questions are a lot, right? You spend most of your time talking about the solution, and then very little of it, they just want to see that you can kind of whiteboard something out. Okay, so the problem. The problem is essentially the minimizing travel distance, right? So this is, if you go on your phone, if you go on Google Maps, if you go on GPS and you try and map the fastest directions to a given point, that is the problem, right? So let's say I'm in New York City, I'm trying to figure out how to get to Philadelphia, right? If I know the cities, I know the highways and whatnot. But let's say I don't, right? What I essentially have to do is come up with a model that figures out how to take, or I have to come up with an algorithm that figures out what path to take, right? Well, let's kind of first figure out what our data points are, right? So the data points are the paths. And now, what do I mean by path? I actually mean roads, right? So the way I'm going to get there is I'm going to get there by roads. Some of them are local roads, some of them are highways and whatnot. At the end of the day, what I'm going to do is I'm going to start a location, I'm going to take a set of roads, and that set of roads is going to lead me to Philadelphia, right? If I don't think about taking me to Philadelphia, I'm just going to think about where all those roads can take me, right? And so I'm going to use roads and paths interchangeably here. Paths is kind of like the computer science thing. Roads is like the real world problem thing. And it's often important to kind of realize that a lot of these things are very interchangeable. One other thing I'm going to do is I'm going to talk about taking the roads taking you 1 mile away. But if you actually write this algorithm in the real world, you're actually going to do it on a lot smaller of a scale, right? If you're in a city, you're going to take it city block by city block. And you're going to be like, okay, this new city block, I'm going to figure out how far away this road takes me by city blocks, and then I'm going to make a new decision at that point, right? I'm going to say taking me 1 mile away because I think it's mentally easier to think of traveling 1 mile from where you are and then thinking of it as that. But if the other way of thinking about it is easier, thinking about it that way because that's definitely more accurate. Okay. So let's talk about like a brute force algorithm, right? I have basically I'm in Manhattan. I'm in Greenwich Village or whatever. I essentially want to figure out, based on this road network that I have, how to get to Philadelphia. The brute force solution is essentially let's try out every single possible path until we get one that leads to Philadelphia, right? So what I'm going to do is I'm going to drive 1 mile away in each direction, or following every single set of roads. And then at that point, I'm going to go 1 mile again further. And eventually I'm going to like have all abstract set of paths kind of grow away from New York City until one of those paths hits Philadelphia. Once one of those paths hits Philadelphia, that's the shortest path and done. Right? I'm going to pause there to make sure that everyone kind of understands that algorithm.
Yep.
Cool. Okay. So it's a very inefficient algorithm, right? The big part of that is you're going to be exploring paths that are like, you're going to be going north in one of those paths, right? And intuitively, you should be like, okay, there's no way the path going north is going to lead me the fastest to Philadelphia, but there's no way you've told that algorithm to do it that way quickly, right? You're going to end up exploring Connecticut, Long Island, which are absolutely the worst ways to kind of explore. Right. So what we want something is that we do still want to explore all potential paths, but we want to essentially prioritize the better one. And so that's how we kind of structure our algorithm to do it, to explore it in an effective way, as opposed to just exploring all options. Yeah, so I also talk a little bit about the greedy algorithm for this, right? What would the greedy algorithm for this be, right? I'm in Greenwich Village. The greedy algorithm is figure out which direction Philadelphia is and start driving in that direction, right? And that's it. You're going just down one path, right? And the problem there is if you are in Manhattan, you might end up in the southern tip of Manhattan, and you're like, well, in order to get to Philadelphia, you have to drive across water. There's no way to get to Philadelphia. This problem's impossible. So, John, did you understand that explanation of the greedy algorithm?
Sort of, not 100%. I will say that.
Okay, so let me try explaining it once more, and then if that doesn't work, I'll explain it. We'll hop to another problem and see if that works. Right. So let's say my location is Fidei, right? Intuitively knowing geography, you'll know that you have to get out of the city by either the bridges or the tunnels, right? And so the algorithm you write has to kind of explore, has to figure out that the first steps to getting out of the city isn't to just go directly in the direction of Philadelphia, it's to get right? And so
now you cut it out.
The first algorithm we proposed of exploring all paths. Are you hearing me? Hello?
Yeah, Matt, you're going in and out. I think You said the first path to going to Philadelphia is not really, and then a cutoff.
I stopped my video. Hopefully that's gonna help. I think I'm just running anything.
Okay, cool. Yeah.
Is this better or no?
Totally.
Yeah.
Okay. Awesome. So what I was saying, right? So it's telling me I have issues. Are you guys hearing me well?
Did we lose him completely?
You're cutting out like a little bit, but it's like sporadic.
Okay, it seems to be fine. I have like a video connection thing on Discord, so I'll monitor that and see how it goes. So we're talking about if you're like in FIDI and you're trying to get to Philadelphia, right? So in the first algorithm that we talked about, of exploring all possible paths, you're going to succeed in exploring all paths, and so you're eventually going to get out of the city, right? You're going to mentally try and go through every single set of roads that you could take, and eventually one of them is going to reach your destination. If you're trying to do the greedy algorithm, which is I'm going to locally optimize my solution, and I'm going to take a step in that direction, right? So if I start in FIDI, right, in like the center of FIDI, and I'm like, okay, where's Philadelphia? It's southwest of me. Okay, I can either go south or west because that's where blocks go. Okay, I'm going to go south, right? And that is the locally optimal solution, right? I'm getting closer to my destination, right? Then, right, I'm going to keep going south, south, south until I hit the water. Then I'm going to keep going west until I hit the water. And then I'm like, okay, I am locally as close to Philadelphia as I can ever get. I'm locally optimal.
Okay.
And so in order to actually leave the city, I actually have to make a decision that isn't locally optimal. I have to go further away from the city before I start going. I have to go further away from Philadelphia before I start going closer to Philadelphia.
Okay.
And so that's the local optimal.
So is the purpose then, Matt, that we know it may not be the optimal solution, but you need to just, like, I guess I'm just trying to understand what would be a real use case of using greedy algorithm. So going for a quick and dirty solution that may not be optimal. So like from a neural network standpoint or something, and that's when these get used more. Like when we're talking about.
I mean, so it depends what the problem is, and it also depends somewhat on what the business case is. There's a set of problems called the NP complete problems that doesn't have an efficient solution that runs like efficiently in the sense of something that like a computer can reasonably do. Those problems are often just solved as greedy algorithms, simply because you're like, okay, I'm gonna spend a year computing time trying to figure out the solution, or I could spend an hour of computing time getting a roughly right solution that is good enough. All right, let's go with the roughly accurate solution, right? Those are the trade-offs. There's a lot to say about local optimization in machine learning. A big pitfall of a lot of people's machine learning algorithms is optimized to either a local constraint or they're optimized to a test data set that isn't actually indicative of your production data set. So there is a lot of pitfalls, but it's also like, take each problem as it is and sort of figure it out.
So Matt, you're going in and out, and we're hearing every other word. I don't know if you guys, Evan or Tom, if you're experiencing the same thing.
It doesn't seem as bad for me as it's coming across for you. I'm still getting most of the sentences.
Yeah, me too.
Okay.
Is there something you missed, John, that I can repeat?
Matt, carry on. It's like Evan's saying that it's okay, and if we're feeling it's okay, then it might be just my.
I do think Tom is feeding back pretty hard, though.
I'm sorry?
Are you on like speaker or something? Because it's feeding back.
Is it really? I don't have a speaker on.
Yeah. I don't know. Strange.
Yeah, I heard that twice.
That's funny.
That seems to work. Awesome. Oh, no. Tom, do you mind muting yourself?
Yeah. Yep.
All right.
Yeah, so if you can see the text too, and you have questions about the text, that can also be helpful. So let me kind of sketch out a different algorithm that is the dynamic programming solution to this. And what it essentially uses is a tool that comes up with the direct driving distance, right? So well, it's not the direct driving distance, it's essentially the direct distance, right? How can I, like if I flew as a bird or as a plane or whatever, from New York to Philadelphia, how far away from New York am I? Or from how far away from Philadelphia am I? And what this is going to allow us to do is help prioritize our other solution set in such a way that we are really only searching for very optimal solutions. And so what does that look like? First, what we're going to do is we're going to take our location and we're going to take our and we're going to take the distance from us to New York, or we're going to take the distance from our current location to Philadelphia. That's what I meant to say, right? And that is what I'm going to call total distance, right? That total distance is going to, when we define it later, it's going to include the distance we've driven up until that point. And since we haven't driven any distance, it's just going to be our direct distance from that. We're going to take those three values, and we're going to push them into an array. Then we're going to essentially go through that array, and that array is going to represent all the possible paths we've gotten to and the locations that they've gotten us to, right? And the time to take us there, those three values, right? So what we do is we pop off from that array, we take a value from there, and then from that location, which the first time around is just going to be our start location, we take all paths, and let's say all paths that take us a mile away, right? So we're going to draw a little circle around our location in Greenwich Village. It's essentially a mile circle, and we're going to look at all those locations. Then what we're going to do is we're going to take that location and compute the direct distance to Philadelphia, right? So if I've driven directly towards Philadelphia, I'm going to be a mile closer to Philadelphia. If I've driven a mile away from Philadelphia, I'm going to be a mile further away from Philadelphia, right? And what we're going to do is we're going to take that number, which is total distance, and add it to the distance traveled, which at this point is 1 mile, and we're going to add all of those values into that array, ordered based on that last value I wrote out, right? So the next thing in our array is going to be the value that was us driving 1 mile directly towards Philadelphia. The last thing in our array is going to be the one that is drive 1 mile away from Philadelphia, right? And then all other options are going to be somewhere in that based on how they fall relative to Philadelphia. I'm going to pause there because I don't think I explained that super well, but let's see if there's a question.
I'm good. I think it makes sense so far.
I mean, so that's the big hurdle of the problem. You guys want to hop to the code? So at that point, it really is pop off the most recent thing from that array and repeat the algorithm, right? So we're going to pop off our step 2 in this loop is going to be, okay, we're a mile towards Philadelphia. Now let's figure out all locations a mile around me. Let's figure out all locations a mile around me, and then let's add all of those arrays into the value. What's going to happen is if we end up hitting the tip of Manhattan, eventually we're not going to be able to keep adding arrays that go closer in that direction, right? So we're going to stop exploring just going south, and we're going to start exploring all other options. Again, the ones that are going northeast are going to be explored all the way at the end, and the ones that are just going west and just going south are going to be explored earlier, right? Because they're a lot faster in that direction. I'll touch on these notes a little bit later. But
so, Matt, sorry, just one thing. So programmatically, before we get into the code itself, does that mean we need to have like two set of counters, one that's incrementing, the other one that's decrementing, like the problem that Edwin had solved last time of like how much you can fill within these balls or whatever that was, right? How much water you can fill within this ball, the maximum of water. So is that the general thought that increments, one decrements, and then you just measure which?
No, there's 3 values that we're measuring. One is location, right? So that's going to be a set of coordinates.
Sure.
Right. Then we're measuring the distance we've traveled so far, right? So the coordinate has to correspond to a distance traveled so far, right? In order to get to this location, you need to have traveled 4 miles.
Yeah.
Right. And then it's like, then the next question is, okay, if now I'm trying to figure out how to get from this location to Philadelphia, how likely is it that this is going to be the optimal solution? Right? So what I'm going to do is I'm going to draw the direct distance, right, as it is on a map. I'm going to add it to the distance I've traveled. I'm going to say if this number is small, it's likely that this is going to be, it's possible that this is going to be a good path. If this number is high, that means I'm likely going in the opposite direction, because as I'm traveling, my direct distance is either not decreasing or it's not decreasing fast enough to like compete with other paths.
Got it. Okay.
Okay. So I've essentially mocked out a problem. I have 3, like when I mocked it out, this is like the meat of the problem, and then there's these 3 other functions that could be relevant. Direct distance to Philadelphia, right? If you have coordinates, you just simply do some sort of complex geometry on a globe or whatever. You probably import it from some math function or something. Explore paths, what that's going to do is it's going to take a location and then it's going to find other locations that are within a mile, right? If we're actually doing the real world example, that's going to be, I'm going to actually find out what street I'm on. The location is going to be like the coordinate in the street I'm on. And then it's going to be like, what if I take it 1 block there? Or what if I take this highway 1 exit further, right? And so that's going to come up with the next quote unquote location that I can be. This ordered list insert function is a little bit more complicated, but it essentially talks about like I'm going to bring up a data structure called a priority queue. And what a priority queue is it's a list that always stays sorted based on 1 value, right? And so in this case, that 1 value is what I'm calling total distance, right? And total distance is the distance I've traveled plus the distance that a crow would fly to Philadelphia. All right, let's go through the algorithm. All right, so I'm going to initialize, I'm going to get some direct distance from my current location, right? This is going to be Greenwich Village, Manhattan, right? And then I'm going to get the direct distance to Manhattan, or to Philadelphia. Then I'm going to push it onto, I'm going to initialize this array to be essentially that. It's got 3 values. It's got my current location. It's got the direct distance that I just talked about. And it's got 0, which represents the distance I've traveled so far. Okay. Then, while there are paths still left to explore, that's essentially what these represent, paths, I'm going to pop off the most recent one, or I'm going to pop off the one with the lowest. I say direct distance here, and then I call it total distance there, right? So direct distance is going to be, or total distance is direct distance plus distance traveled. In this case, it's 0, right? So those in the initial set, in the initial iteration, direct distance and total distance are the same, but that's not going to be the case for the future. All right, so we get location. This is sorted based on total distance. And then we have the distance we've traveled so far. What we're going to do is we're going to go through every single location that our explore paths function takes us through, and what that function does is just explores either 1 mile away or 1 street down, gets a new set of locations from that far away. Then you get your new total distance, which is the direct distance to there plus the distance you've traveled plus the 1 mile you just traveled. Right? And then it's going to add into that array. And then it's going to add into that array based on that total distance value, right? So we're always minimizing the total distance value.
Yeah, gotcha. Could you maybe point out particularly where the minimization is happening?
So it's happening in this ordered list insert, right? So by maintaining the total distance number and doing only a minimum of it, I'm only going through things that are most directly there. Let me grab a pen and paper. Right. So the thing to kind of highlight with this algorithm, grab a sheet of paper. Right. I'm going to draw something that I think is helpful.
Oh man, you're hitting the space bar.
Am I?
Yeah.
Control Z that.
Apparently. Do I want a... How do I draw this? Does anyone have a good drawing tool online? Do I have access to lucid charts?
Oh, diagram.io, I think, is a good one, maybe.
Diagram.io.
Let me see.
I guess my question is, I just don't see particularly in the code, like there isn't like a min function. So I think just saying that it's being minimized is kind of vague in that respect. So I think other viewers would maybe have that same question.
Yes. Do you understand how the algorithm works? Because I think there is still, I don't know if I quite explained it as well as I would like.
So Matt, I think I really understood the time you were like, if paths equal, like put in this array, location, distance plus 0, 0. The piece where I'm still sort of stuck is what Evan's saying, but also if you say when len paths is greater than 0, location comma total distance, which is direct distance plus 0 in it. Then distance traveled equal paths dot.
In this one, okay.
What are you pop? And you said that take the smallest.
I don't know if pop is a Python function. So
yeah.
Oh, it is. So paths is meant to be an ordered array, in the sense that it is always going to be ordered by total distance. This total distance value represents, so I'm going to draw essentially a few triangles, and I'll show you guys what I hopefully mean. In there.
So what pop does in Python is return the last item of a list.
That's right. That's right.
Is the same thing that you're thinking?
Yeah, I mean, you order the list based on like the last item has to be one that minimizes total distance.
Okay.
So you're saying it's sorted, and then that's why it's the last one is the lowest, and so up that.
Yeah. So as long you have to maintain order in your array, and that's where the minimization is happening, right? Your next step is the minimum one.
So that's wrapped up in the function ordered list insert that sorting is happening there.
Yeah. All right. You guys see this? Right. So imagine this node is New York. This node is Philadelphia.
Matt, I think you need to switch screens.
I need it. Well,
sorry, we're driving you crazy.
No, I hope it. I always feel underprepared. It's really what frustrates me. I mean, it's not I prepare. Diagram.io isn't working for me. Let's see if lucid chart is. Permission denied on lucid chart. What's going on? What is going on there?
Oh, Matt can't catch a break, man.
I'm going to sign up. All right, let's go through the sign up process real quick. Let's see Google. Awesome. Sweet. Awesome. That's fine. All right, you guys see Lucy's chart?
Yep.
Yeah.
Cool.
Yep.
Awesome. What I want to do, let's use circles. Circle, circle, right? This is New York. Let's do it geographically correct. This is Philadelphia, right? So if this was a simple,
see anything. I'm sorry, Matt.
Evan, Tom, do you guys see it?
I see it.
Yep. You know,
it's on YouTube. It's on YouTube. So if you want to follow along, right? Why isn't this directly? Stop doing.
You gotta drag it into the red circle.
The red circle?
What's the red
Arrow.
circle?
Like, click and drag that. Yeah, you see that?
Yeah,
Oh,
the
yeah,
line to stop going rigid.
You want it to
This-
curve?
Yeah, is there a curve function?
Yeah, right.
I think you gotta grab it in the middle. There you go, yeah.
Okay. Okay. Nice. Okay, we got some very smooth lines that. All right, let's see. Great.
The chart
That
expert.
nice. Right. So this is a direct path to Philadelphia. This is actually not possible, right? Because we eventually hit a body of water. What we essentially want to do is we want to take other paths that go initially a bit out of the way, and then eventually just start taking us to Philadelphia, right? That's the one that takes us on the highway. That's the one that takes us through the tunnel, right? Then let's say we want to take one that actually goes through the GW bridge, right? So let's also make that curved, but it's like that, right? So this one we've talked about being impossible, right? Then we have to kind of figure out of these two paths, which one is better, right? But we also only get to figure it out 1 mile in, right? So we're 1 mile in here and we're 1 mile in there, right? And based on these two locations, we essentially have to figure out which of them is better, right? So what we do is we take our distance to Philadelphia and we compare them, right? And whichever one is smaller, we want to take. But then we also want to note that it's important to think about this other path, right? What if we had gone down this path and we had been over here, right? This is actually closer to Philadelphia than our optimal solution. But the problem with this point right here is we've already traveled so far. And so what we want to do is we're going to take the exact value for what we've traveled so far, and we're going to take an approximation for how far we have to travel left, right? And the sum of those values is essentially what we want to go through and iterate through minimally. Has this helped?
Yeah. That makes a little bit more sense. I think I was just getting wrapped up in the code itself, and I was like, where is this minimization happening in the code? I don't see a min function. I don't see this kind of function or that. So that's the part that raised the question for me. I think it was just the abstraction, though.
Yeah, I mean, I definitely feel that. I do want to point out that if I was asked this in an interview, this is literally what I would write, though. I would, right, like the structuring of the problem is essentially inside this function, and then like everything else is just using, right, this ordered list function is just using what's called a priority queue.
Also, you should expect, like, all traditional search algorithm problems, like, you can never just call, like, min of anything. It's not like modern, like, machine learning where you can just minimize over a vector.
Oh, yeah, I mean, I totally understand that. I think I literally just, like, the ordered list function, I might have missed it on the screen. Just didn't know it was going on in there.
So I have a problem that's a lot simpler. It's called the rod thing problem that we're going to go through in a second. Um, the only reason I brought this one up is because it's like a very applicable real world one. And so, yeah, you will see a lot more of the code and it'll actually solve the problem.
All right, cool.
And I solved it in Google spreadsheets, which is funny. But I think it'll be a great way of explaining why one of them solves it is a more efficient solution.
So Matt, I'm still not able to see the screen. If you don't mind, after the class, if you could just maybe tomorrow or something, just send a screenshot of that. That would be helpful.
Yeah, here, let me.
No,
John, I can see the screen.
Yeah, I don't know. It's something on my side, maybe.
don't worry about it, Justin. I send it to you tomorrow. What do you need? Just this screenshot of this?
Yeah, like I see this smaller version, but I don't see when I try to expand it. It just shows me 2 dots that are dancing.
Oh, you're getting a loading screen.
Oh.
Do you see it in chat? I just sent out what I was talking about.
If you don't let me stop, just continue. I'll catch along.
Yeah, yeah, and when we go through the other problems, that'll be a lot easier. What are my notes about this? The importance of taking the new direct distance variable plays in making this problem faster. Right, so if we didn't have this function that essentially gets us this crow's flag, like what is the direct distance from our current location to Philadelphia, this algorithm falls apart, right? And so that new function plays a critical role in actually being able to make us approach this dynamic programming solution. So then I want to talk about what would it have to change into a problem for this problem to actually involve a mathematical solution? And so what if this was a smooth world with no roads or obstacles, right? Then it's literally the problem of which way is Philadelphia and going in that direction, right? And that's like a very trivial problem, but there is like this parallel to a abstract math problem that parallels the solution that can help us gain insight, even if it's not always a one-to-one parallel. And then at this point of exploring 1 mile away, I touched on this in the beginning. I was saying 1 mile away because I think it's simpler to say, but the actual algorithm in Google Maps is going to be something like let's travel 1 street down in each direction and then figure out that location. So that's about it for the minimum travel distance one. The other one I want to talk about in a high level is the Fibonacci sequence. This is like one of my all-time favorite problems to talk about. And the thing is that it can be solved, right? This is the Fibonacci formula, and f of n is equal to the sum of the 2 previous values, where the first 2 values in this sequence are 0 and 1. All right, so it goes 0, 1, 1.
Move your screen again.
You're right.
Sorry.
No, thank you. I'm frustrating myself. Yeah. Okay. All right. So this is the Fibonacci sequence. Recursive. It looks like a recursive. Yeah. So if you solve it as a recursive problem, this is actually the functional solution. The problem is you go down every path multiple times. Like if you solve for f of 2, you're going to go down and you're going to be like, okay, then I want to solve Fibonacci of 1 and Fibonacci of 0. Oh, let me solve Fibonacci of 1. I'm going to go in here. Well, then I'm going to return. But like, let's say I was at Fibonacci of 4. Right? I'm going to go down and I'm going to try Fibonacci of 3, Fibonacci of 2. When I go down Fibonacci of 3, I'm going to call Fibonacci of 2 again. Right? If I go down this path twice, it's going to be the same as going down this path once. Right? Because this path adds minus is 1, this path minus is 2. And there's actually, like when I was looking at leak code, a lot of the dynamic programming problems that they labeled are essentially just Fibonacci problems labeled by another way, right? So I think the one I saw that most stuck out is a stair stepper one, min cost stair climb, right? So it's either you could take 1 step or 2 steps to get to your location. Step cost. No, that's not it. But there was like a few algorithms where I'm like, this is literally just the Fibonacci sequence by another name. Um, and so this problem comes up a lot. And it actually has a mathematical solution. And the mathematical solution is essentially what's called the magic ratio, the number phi raised to the power of n is approximately the answer. And there's like a whole lot of linear algebra you can do to solve it, which is very interesting. But it's also like if you literally just memorize, or if you just catch the solution at a given step, you have it just as efficient as the mathematical solution. So that's for that reason I would love to talk about it, but ultimately like the math side of it is interesting but not super relevant. The dynamic programming solution is just as effective.
So is recursion sort of a prerequisite? Like, do you need to have a good understanding of recursion in order to be able to do some form of dynamic programming?
On some level, yes. On some level, so they.
I would say 100% yes. It's an absolute necessity.
Okay. Yeah. Let's just leave it at that. Okay.
But also, Jordan, you sort of need recursion for like almost any, like, comfortable with a lot of programming. You need to become comfortable with recursion.
Got it. Thank you.
Let's talk about this rod cutting problem. This was just shamelessly stolen from a website that did a good job of describing it. So I'm literally just going to go through this website's explanation of the problem. So what it essentially is we're given a rod of a certain length, and we're given a set of prices for corresponding lengths. So and then the problem just simply asks us to cut the rod in such a way that optimizes for price, right? So in this case, the input is just simply all the lengths, which is 1, 2, 3, 4. Those correspond to the price, right? So if I have a rod of length 1, I can sell it for 1. If I have a rod of length 2, I can sell it for 5. If I have a rod of length 3, I can sell it for 8. If I have a rod of length 4, I can sell it for 9, and whatnot. If this price function was a mathematical function, I could just do some calculus on that function and solve it. The reason I have to do something more different than just math is because this is a discrete function, not a continuous function. Right? I'm saying 1 maps to 1, 2 maps to 5, 3 maps to 8, 4 maps to 9, 5 maps to 10. I throw that in there as like an interesting point. It's not necessary to understand. Right? And so this is one way of going about it. If given a rod of length 4, what I'm going to do is I'm going to go through all possible cuts and figure out what the value of those are. Right? So I'm going to say a cut of price 4 is going to be 9. A cut of price 1, a cut of size 1 and 3 is going to be 9. A cut of 2 and 2 is going to be valued at 10, which is ultimately our solution. A cut of 3 and 1 is going to be 9, it's the corresponding inverse of that one, and so on. Right? And it doesn't seem like that inefficient of a solution because we all only have, like 7 or 8 of these. But our rod length is very small relative to our actual problem. Okay. So let me show you what that looks like for a bigger rod. Right? And I'm actually going to show you how I solve this in Google Sheets. Because I think that might be helpful. Okay. These are just some values that don't really matter. I'm going to hide these for a second. Doesn't matter. Okay. So I have the same values, right? This is the size. The wrong size goes up 1, 2, 3, 4, 5, 6, 7, 8. And then the values 2, 5, 8, 9, 17, or 10, 17, 17, 20. Then what I essentially do is I generate every possible combination of those that I can cut it in, right? So I generate one where I just cut it where I just take a size of cut one size of cut 2, 3, 4, 5. And this list gets so big because going through every single possibility is endless. Now, some of these are essentially useless, right? We should know that if I can go up to, if the size we're solving for is 7, and if I'm looking at sizes of cuts 1, a size of cut 6, a size of cut 5, or say again, 5 numbers of cut of size 1 or 5 rods of size 1 are going to be definitely worse than 7 sizes of rod 1. So we go through some unnecessary solutions, but this is kind of like, what if we went through all of the problems? And at the end of the day, this solution ends up going through like 1,500 lines before we actually go through the last iteration on this problem. So, I mean, what are the actual algorithms in this? This one, all it does is take the corresponding sum product of our price row, right? So given 1, I multiply it by the price and whatnot, right? What I also did was include a column of whether or not it passes constraint that does something very similar, right? It takes the corresponding sum product, but instead of the prices, it takes the sizes and then makes sure it's less than the size, right? And so some of these, like this one, a cut of size 6 cuts of size 1 and 1 cut of size 2 would not be valid. Right, and the reason it's not valid is because it's too big for one of our constraints. Right, and so it's not included and whatnot. Okay. Does this kind of solution make sense of trying everything out and then seeing if it works? Or seeing what the maximum is? And Evan, to kind of touch on your point of where the max is here. Right, this is a max. It's actually a max if. But yeah, I'm maximizing across the total values.
Gotcha. So you're doing, okay.
Right, so maximizing across here, this is going to be a product across, right, is the product if, or the sum product.
What is your constraint again? Like what will turn it true?
If it's less than the size. All right, so I had trouble kind of generating all of these possible scenarios. What I ended up doing was I'll show you what I ended up doing. What I ended up doing is figuring out the max number that I could include in an array and essentially counting up to that value. Right, so I count up to 7 every single time in this row, and in this row I count up to 3, but I take 7 iterations before I count up to it. Right, so I go 0, 0, 0 7 times, and then I go 1 7 times, and then I go 2 7 times, and then I go 3 7 times, and then I go 0 7 times, and so on and so forth. This was a bit interesting to write, but
Yeah, wow.
I mean, the other thing to point out is that you really can model anything in Excel. At a certain point, it starts to look dumb, and the formulas you use are like, I'd rather just use a hardcore language. But the point of doing in Excel was literally showing you that every single, the brute force option is literally trying every single option, and this is the option set, and then trying everything, figuring out this maximum value here, and then figuring out the corresponding price of it, and then taking the maximum of those prices. Okay. Let's go to the Google Sheets version of this. So I'm taking that same problem, but I structure the problem differently. And so what I essentially do is I come up with a base case, which in this case is 0. And I say I can only sell this for 0, right? Then what do I do at 1? Size 1. Well, size 1 is basically the same thing, right? I can only sell it for size 1. All right. When I have a rod of size 2, I have 2 options, right? So what I can either do is I can sell it for a rod of size 2. In this case, it's going to be a sell for 3. Or I can sell it for a rod of size 1. If it's a rod of size 1, what I do is I go to this corresponding problem, right? I go to the solution at size 1, rod size 1. And then I'm like, okay, I've already solved the rod size 1, so this is going to be this 2 plus the solution at that, going to be 2. Right?
Gotcha.
Let's go to 3, right? So again, 3, if I sell it for at size 1, right, it's going to be 2 plus the solution at size 2, which is going to be 4. If I sell it at size 2, now let's look at this, right? The solution at size 2, over rod length 3, if I sell it at size 2, is going to be this value of 3 plus the maximum solution of a rod of size 1, right? Because I'm cutting 2 off to get this 3. If I sell it for size 7, or if I sell it at size 3, I don't get to sell it for anything else. I just take the solution at size 0, right, which is 0. And then I take this value. And then what I do is, in order to do the actual maximization, I try all of those values. I take the maximum of all of those options. And it turns out the best way to sell a rod of size 3 is to is to just sell it at size 3 and get a profit of 7. I changed up the numbers, by the way, if that confuses anyone.
Oh, based on the set solution?
Yeah, let me paste in those numbers again. Just keep it consistent. And I can show you that these numbers add up. Everything's going to take a second to update. Yeah,
So
update.
fast. I hate to be that guy, but can you walk through, like, maybe just the first 2 one more time?
Yeah, okay. So let's go back to even the simplest one, right? 0, if I have a rod of length 0, it's size 0. If I have a rod of length 1, I'm selling it for 1. Or I'm selling it as the size of rod length 1, which has a price of 2. Right? So these 2 values are trivial. What happens if I have a rod of length 2? I essentially have to decide if I want to cut it or not. If I don't cut it, I get a value of 5, which is essentially the value, the price I'm getting for it here, plus a rod length of 0, right? Because if I get rid of the 2 inches that I have no rod left, and I sum up 2.
Gotcha. Okay.
Whereas, if I did 4, I have 1 inch left, so I add up 2, and at 1 inch I also have 2, so that would be a value of 4, and so and then I take the maximum of 5. So, I'll share this with you guys, but like,
Gotcha.
let's look at how these numbers change, right? Let's look at the numbers highlighted, right? So, this A7 is greater than D1. What that's essentially testing is, can I sell it for that price, right? The rod length is 2, and I'm trying to sell it for 2. That's great. If in this case, right, like if I'm trying to sell it for 3 and it's a rod length 3, it's just going to be blank. Right? So that's the only reason those 2 numbers are relevant. Whereas these numbers like D2 is the price, B5 is the solution if I took away the amount that I'm talking about, right? So I have a rod length 2, talking about taking away 2, I'm going to look up the rod length of 0 and find the solution at 0. It's going to be 0, so all I'm doing is selling it for its current length. Let's say I start increasing the rod length, keep talking about cutting off 2, right? I have a rod length of 3, talking about cutting off 2, so what I'm going to do is I'm going to add 5 to what the rod length of 1, the optimal solution at the rod length of 1. Same thing for 4, right? If I have 4, when I talk about cutting off 2, and so on and so forth. And this is where I try out all the possible scenarios, right? I try out cutting off 1, I try out cutting off 2, I try out cutting off 3, cutting off 4, and then I essentially just maximize it. But when I'm already talking about the next level, like when I'm talking about cutting off 1 inch and getting this value, this one's already optimized. Right here, it's already optimized. Right, this a rod length of 3 is the maximum value you can get out of it is 8. Right, so what were we talking about here? We were talking about a solution set of size 7 that literally made up 1,500 possible options. Of those options, 44 were not blank. And in this case, line 12 is already what I'm talking about, rod length of 7.
Matt, can you just hold there for just a minute? Can I just process that just for 1 minute, what you did at
Sure.
7 without explaining? Sorry, just 1 second.
If you guys paste your emails in chat, I can also share this document with you guys.
Will do. I mean, I think generally I like this approach to like trying to break down a recursive problem, because I think even just like as someone who has to like study lead code for interviews once in a while, when it comes to recursion, I very much find myself memorizing how to do certain problems more so than, you know, understanding deeply how recursion works, or, you know, what's going on each step of the way. I think it's a really good way to start like addressing that and like approaching that. I do think we can like iterate on this and maybe like simplify it. I don't know, for some reason it is like just the problem of recursion is hard to wrap your head around.
Yeah.
But I would like to definitely see if like you were to iterate on this and like think of like a simpler, even way to present it. I think it could be like incredibly beneficial as a learning tool.
I'll double that. Yeah, I'm with Evan.
Yeah, so I'll touch a little bit on that. There's 2 things I want to talk about. One is, I mentioned this point of dynamic programming, and this is also somewhat true for recursion, is about appropriately defining your solution. And so that's going to get to my second point, which is starting with a base case, right? So in my set solution answer, the notion of a base case does not exist, right? Why? Because I come up with all possible scenarios, and I never talk about a rod of length 0. I never talk about a rod of length 2 or 1 or whatever. I only talk about a rod of length a rod of length 7, right? I'm only talking about that. Whereas in the dynamic programming problem, I am kind of trying to break it down into its smaller parts and then build it back up, right? And in that case, the best place to start is your base cases, right? In this case, it's either the 0 length or the 1 length. I included the 0 length because even though it's trivial, it's important to talk about, right? Or it makes mathematical sense. The value 0 here still makes sense, right? So if I have a rod of length 0, I sell it for a value of 0, right? That should be kind of trivial. If I have a rod of length 1, I sell it literally as a rod of length 1, or as a rod of length 1 and make a value of 2, right? So these 2 values should be very, like there should be a mental hurdle right here. The mental hurdle is literally on line 2 or on line 7, right? When we're talking about a rod of length 7. It feels like there's going to be a dozen more mental hurdles, right? No, the only mental hurdle to think about is this one right here. In fact, all I'm going to do, I want to delete all of these, right? Because those don't matter, right? And so this should be a bit less overwhelming.
Totally.
So we're talking about the rod of length 2. What is its solution going to be? Well, its solution is the max of all options, right? I can cut off 1, and that's going to be this value. You cut off 2, it's going to be this value. There's no other values there, right? What happens if I cut off a length 1? Well, I gain a value of 2, and then I also have a rod of length 1 remaining, so I'm going to find the solution for a rod of length 1. The same is true for cutting off 2. All right, now let's do, does this work? No. I think that's right. All right, and so now here are the hurdle going from 2 to 3. It's the same hurdle that you have to make at length 2, right? So even though I'm adding a new line, and even though there's going to be more numbers and a new value becomes possible, it's the same hurdle. And that's essentially saying, what I want to do is I want to maximize across all of my solution space. My solution space, I'm going to make it as small as possible. I'm only going to figure out what the next rod I'm cutting, right? that is either a size 1, a size 2, or a size 3 rod. If it's a size 1 rod, I have to figure out, I have to cut off one of the size 1, and then I go to the solution at size 2, which is 5, and 5 plus that gets me 7. Right? And then the recursion actually happens here, right? I cut the value, I get to 5, and then I figure out where 5 is. I go here and I go to 0. So this solution is going to be cutting off a 1 and then cutting off a 2. Do you understand how I got there?
So it finds out that, okay, if I have a 3, the max value at 3 is 7 because I'm going to cut off a 1. And now you have 2, so now you're starting to recur. So now you're saying, okay, now I'm at 2, so what is my max solution when I'm at 2? And that turns out to be 5 at that point.
Yeah, which is cutting off 2 and then so on. And that's why it's not a coincidence that these two values are the same. Right? Let's follow this value. Right? What this value does, it takes me here. I have a value of 5. Let's find out which one got me 5. Well, it's the value of 2. Oh, look at that. I took off a 1 and then a 2. Well, here, what I did was I took off a 2, and I got here, and then, oh, look, I took off a 1. Right? So I explored both scenarios, but after I've gotten to this scenario, these values reconverge. So we can actually see that if we go through some bigger numbers, and even just 4 is going to be enough for us.
Awesome. This is it, man. Like, this is, you're doing it.
Right? So, yeah, I know it was overwhelming initially. And I do think, like, this grid is super important to think about when you're thinking about dynamic programming problems. It can help with recursion. The distinction I'm going to make is that you often, like, recursion problems, you don't think of in 2 dimensions. Dynamic programming problems, you will always get this kind of 2-dimensional thing where this thing is going to point to another thing, right? So let's say we have a rod of length 1. I cut off 1. I get taken to 8, right? That's going to be this one of size 3, and this one's this one's going to take me to 0. Well, all of them are going to take me to 0. Oh, I don't get this quite yet. Let's try 5. So I'm trying to point out these values end up reconverging. And I think at 5 that might be the case. Let's see what 13 and 13 are. So if I take off a rod of length 2, I'm going to come here and I'm going to end up taking off a rod of length 3. And then I go back to 0. They reconverge at 0, so I'm not able to kind of point out the benefit of this reconvergence. But if I were, let's just take hypothetically, right? Like, let's think about this abstractly. If I had any length rod and I took off a size of length 2 and then a size of length 3, it should not be different than if I took off a size of length 3 and then a size of length 2. Order does not matter here, right? And if you follow these eventually, what you end up doing is you follow this line of rod length, right? We took off 2 inches. We have 3 inches. We follow this one. We take off 3 inches. We go to 0, and we converge back at this point. Following the 3 path, we follow the same path. We take off 3 inches, and we're at a rod of length 2. And then we take off 2 inches, and we end up following this path there directly. And so it converges there very quickly. Let me see if I can mess with these numbers a lot. That should make this easier. 15, 14, 14. There we go. Nice. Okay. If I take off this new algorithm, if I take off a rod of length 5, it has an optimal value of 15. If I take off 1 inch, I'd solve for a rod at 4. Going to be any of these. This is not. Hold on. There we go. There. I hope that's right. Right. Okay. I'm trying to play with the numbers to demonstrate the phenomenon I'm trying to get at. It's a little bit tricky. And Tom just sent me some passwords or some emails, so I'm going to share with you guys. Great. Private.
Thanks, Tom.
Rod.
No problema.
Okay.
Evan, please get a Gmail.
I'm sorry, I have a Gmail. It's so full of junk at this point that I've just, I switched over to my Apple email for all other things. I didn't realize it was a pain in the ass, though.
No worries. Okay. So what I did by changing these numbers is I made it more efficient to take the lower number cuts so that I have more lower number cuts in the final solution. And so we'd see that if I have a 5-inch rod, but my first cut is 1 inch versus if my first cut is 2 inch, it doesn't matter. The reason it's not going to matter is because the final solution is going to have both a 1-inch cut and a 2-inch cut. Right? Let's follow the 1-inch cut right now. Right? We get here to 14. We cut off 1 inch. We get a rod of length 4. And then we find the optimal solution, which is going to show that we want to cut off a rod of length 2. And it's going to go to a rod of length 2, and we want to take another cut of rod length 2. Fine. What if we're taking off 2 inches? Then we want to go to 10, and we're going to come back here. We're going to go to the rod of length 3. We're going to come here. What I was trying to show is ideally this would be the only option. And then if we cut off 1 inch, we ultimately get to the point where we're talking about a rod of length 2. And it doesn't matter whether our first cut is 1 inch and then our second cut is 2 inch, or if our first cut is 2 inch and then our second cut is 1 inch. Eventually we get back to a rod of length 2 after those 2 cuts, and we optimize for that same problem. So both of these 2 paths, even though they take the initial step differently, this one's going to go to rod length 3, and this one's going to go to a rod of length 1 or rod of length 4. After that next step, they both get to a rod of length 2, and then that's like you don't have to try out as many problems.
So Matt, this is very helpful, but I just want to go back, to your original definition.
Sure.
So this solution will work when there is a discrete distribution of the content, meaning know that column 1, let's say whatever that column rod size is 1, price is 3. For the next one, 2, it's 7, 3 is 8, so forth. If it was unknown, then this solution obviously won't work, right? Because we don't know what we're gonna get at, right?
Oh, if you don't have a price that you can't solve this. What that point is to reference is that if this was if price was a function, right? If for every inch of the rod, I gained, like if this was 2, 4, 6, 8, 10, 12, right? At this point, it doesn't matter what we cut it at. All the things, like you even see the numbers start to 6, 8, right? Look how all of these numbers essentially end up being the same value. It doesn't matter what we cut it at. So this is a linear. So this is a linear price thing, a one-to-one thing, and it's actually value. What I really care about is if this was a function that was like differentiable. So if it was a function that was differentiable, we can find a maximum or a minimum, and then use that to figure out a problem, right? So if there's a local maximum, basically saying that one of these values has the best price per inch, then we're going to cut it based on that best price per inch. And so we don't have to do any of this dynamic programming stuff, because all we have to do is solve this continuous function and then come up with our solution. This is also true if we had a rod of length infinity. What we would do is we'd just take our best price per inch, which I think is 17 at 7, and that's all we would cut at, and we would never have to talk about it again. But real-world problems often have discrete constraints, so we have to if we're looking for the actual optimal solution, we can't just use the approximations of like abstract math and continuous math. All right. Let's touch on what the actual. So this is how they described it using math. This is actually the best way. The rod cut of size n is equal to the max of the price of that cut, or the maximum of all potential cuts of that size, right? So the price of, and where I is going to be whatever cut we're talking about. So the price of, well, I don't know why they're iterating 1 to n, but right. So the first price plus the potential if we cut off that price, or if we like the price of 1 inch, and then the solution if we cut off at 1 inch, the price at 2 inches, then the solution if we cut off 2 inches, the price of 3 inches, and then the solution if we cut off 3 inches. It's the exact same phenomenon. And then what does it look like as Python code? Well, it actually looks, this shouldn't look as scary, right? This is defining the problem at the bottom in the main. Why did you do that? I'm going to refresh the page. We define the price, we define the size of the rod, and then we pass in this function, right? And then in this function, if it's if that length is 0, then we return 0. Otherwise, what we're doing is we're trying to take the max value. Line 18, 19 is us doing a max on the thing, and line 16 is us exploring the recursive thing, right? So the corresponding line 16 in the rod problem is each of these individually. And actually, each of these functions essentially looks very similar. The corresponding line 18/19 is the actual max that we do here. I'm going to take a second over here if you guys have questions on what the Python solution is.
Oh, interesting. So
Yep, that makes sense to me.
How's it going, Edwin? Glad we have you.
Yeah, I was a little bit lost because I didn't know what the problem was, but now it all makes sense.
Cool, yeah.
Were you running out?
Yeah, I need to order food now. I'm pretty hungry.
Okay. Since no one was asking questions. Yeah, one of the things I'll talk about is how like some of these functions end up translating, right? So this max that I do across all total values is the corresponding max that we do across these 8 values, right? Why do we have to do a max across 150 values here and we do a max of 8 values? Well, for one, the max is distributed across multiple rows, but more importantly, we are essentially just, well, like the way we structured, the way our values kind of reconverge onto other values, like I was talking about, if we cut off 1 versus if we cut off 2, like which of those happens first doesn't matter. If those paths reconverge, and so we end up having to do a lot less. rather than exploring all 1,500 solutions. This constraint of the size of making sure that we follow size does not exist in this thing. We never check if we're following the size. Why? Well, actually, no, we do. The way we check for it is if we check if we're able to cut off the corresponding length. So we have a rod of length 5. We can cut off 5. All right, and so there's like two things. This is to take the final option or set of possible, the final option, and see if it passes the constraint. The dynamic programming is to never leave the constraint. Our problem never allows us to not have this value, right? And so if we actually left this constraint, even if we left it in some other row, our algorithm would fail, but we have to define, we end up defining the algorithm such that all we have to do is check, oh, are we able to make this cut? Oh, since we're able to make this cut, then we do make this cut. That is us never leaving that constraint. Yeah, and then in this solution, you'll actually be able to find which is the right value. All you have to do is look up the 19 in the here. In this solution, you actually have to recursively kind of trace the values, right? So you have to go, oh, rod of length 5 gives us a value of 10. All right, let's go to cut off 1 and go to 8. Okay, let's cut off another 1. Let's go to 6. Oh, actually, this is the dumbed down version, so it doesn't matter. But yeah, we just keep cutting 1 off. We have to actually follow the solution afterwards.
Could you go back to the Python solution from that webpage real quick?
Sure. Actually, let me.
So maybe this is like fundamental, but it says like rod of length I has a cost price I minus 1. Is that just in this particular situation?
So look how they're doing their range function. It starts at 1 and goes 2 and plus 1.
Okay, so it doesn't start at 0.
Yeah, so that's why the price is off. Why does it work for the rod cut? Well, so the 0th value corresponds to a length of 1, right? So if we were to do this range from 0 to n, we would actually have to cut off an extra inch in our rod cut. So instead of doing the minus 1 here, what they decided to do is, okay, our range is going to go from 1 to whatever. And actually, if you go to line 26, look, their length array starts at 1 and goes to 8, whereas if you were to generate a range, you start at right. So
gotcha.
Yeah, but if you were to try and get the price corresponding to the length of 1, you'd have to go to the 0th value in the price array.
Okay, gotcha.
I can't see one thing, sorry, maybe just my screen. The max value equals float, and it says minus infinity. Is that what it says in the quotes?
Yeah, so that's a general way of doing max. And so, like, what happens if you're trying to take, so what happens with the max value, right? They initialize the max value, and then if they find a better max value, they reassign that value.
Just reassigning. Oh, that makes sense.
Right?
Got it.
And they initialize it to negative infinity just so you start at the lowest possible value. So let's say hypothetically all these values are negative, right? Initializing it to a max value of 0 would be flawed, because then you get a value of 0, whereas no, you're maxing across all negative numbers.
Got it. And I gotta drop off, but thank you so much. This is very helpful. Thank you. Really, really good.
You're absolutely welcome. And
Thank you, Justin.
remember, Sunday I'll be doing some more pair programming. So.
Yes, thank you. Bye, guys.
Bye, Jonathan. All right. Yeah, I mean, that's it. Unless you want to keep looking at the screen, Evan.
No, I kind of get it. Yeah, I don't know.
Algorithms just don't make immediate sense to me. It just takes time for me.
Believe me, it takes a while to actually start seeing it.
Yeah, algorithm
And
is so hard.
Yeah, I think like one question. I don't know if we have an extra 5 minutes. When just looking at like the Fibonacci problem, when I think you had it in VS Code, when you're doing something like returning, um, a recursive function plus another recursive function, I guess kind of like the order of operations there is kind of a mystery to me. Like does the
do a bunch of
do
print
we
statements, man. Let's do it.
do the print statements?
No, seriously. And like this is where it goes back to like me being like, come up with a hypothesis of what you think is gonna print, and let's see if you're right. You know what I mean? Let me write an algorithm, and don't just guess. Like actually step through the code, and tell me what you think is gonna print.
Right.
That's a good one. Yeah, it's cool.
Let me give you 3 different scenarios.
No, I think this is a good point, and it goes back to like first principles when I was initially like trying to learn things. I definitely feel like I have maybe you lose sight of that kind of basic breakdown as you get into like something like recursion. But I think it's a really good idea. Just like print it out.
You want to do it or no?
Yeah, let's do it. I mean, are you gonna run it? Should I throw it in my ID?
I mean,
You have a grandmaster plan here.
Yeah. I mean, okay, let's do Fibonacci, the first one, of, let's say, I think 4 should be in. Oh, yeah, 4. 4 is enough. Yep.
All right, cool.
Let me spin up a terminal. Oh, what's going on here? Function already defined.
Oh, you have the same function name.
Yeah, Fibonacci. Nice. Spin up the terminal. Do you guys have your guesses for the first one?
Wait, what am I guessing exactly?
What's going to print?
If I run this function, Fibonacci, this regular one, what is going to print out? Right, the print and on line 2.
So I think what's going to happen is it's going to do n-1 all the way down until it gets to the bottom of that, and then it's going to do n-2 until it recurs to the bottom of that.
So you think it's going to be... So list out the numbers you actually think it's going to be.
That's harder. I don't know.
Well, so n-1, you're going to start at 4, right? You're going to go -1, you're going to go to 3, right? You're going to go -1, you're going to go to 2. -1, you're going to go to 1.
Exactly.
1 actually hits this endpoint, so it's going to print 1, and it's not going to go to 0, right? Because it's going to hit here when it hits 1, right?
Yep.
Oh,
and then
I see.
What do you think is going to happen?
And then I think it's going to be 4, 2, and then 0, which will return 0.
So you're missing something.
Yeah, definitely missing something.
So it goes 4, 3, 2, 1, which you're right about, and then it has the 2, 0 somewhere in here. But after you've done, let's say you did Fibonacci of 4, and you hit this point where you do n-1. Then you do Fibonacci of 3, right? Then it's going to branch off and do each of these paths individually. So at Fibonacci 3, it's going to go the n-1 route, but it's also going to go the n-2 route, right? So in this case, it's going to be 4, 3, 2, 1, 0, because it went down each of those the 1 paths, and then it's going to go back up to the 2, so it's 4, 3, 2, 1, and then at 2, the Fibonacci of 2, it's going to be like, okay, we solved Fibonacci of 2 minus 1, which is 1, and then I'm going to solve Fibonacci of 2 minus 2, which is 0, and it's going to give us this last 0.
Hmm.
What?
Then it's going to go...
Wait,
yeah.
What? Why?
So
Why does it do that at 2?
It does that at every step. Every time you pass in a number here, it's going to make 2 calls, not just one.
Okay. Gotcha. So that's kind of like, so it is running. I mean, clearly it's not actually running them both at the same time, but
You can see it's running the left. It's running the first Fibonacci function, and it's going to keep recursively calling that, and it's pushing that on the stack, and then it's calling the Fibonacci n-2. Does that make sense? So it's not really in parallel, but it's in the same level in terms of what's called. Does that make sense?
like sort of. I don't know. It's kind of hard.
What's Python's debugger?
PDB. If you just type PDB and hit tab, it'll throw it in. It'll throw it in there.
PDB, right? PDB. PDB.
Dot set trace. Dot set _ trace.
Debug? What is it?
No, the set trace.
Set trace.
Set trace.
Yeah.
Yeah, that looks good.
Right, okay. So I'm at here, it says I'm at Fibonacci with, okay. What is n? Do I get n? Print n.
Nice. Yeah.
Cool. Okay, and what's my next step? It's n, right? I do n.
Yeah.
It's gonna hit this time next time around, right?
Mm-hmm.
Oh no. What's continue? See?
Yeah.
Yeah.
Print n. I already continued. Right, so I'm at 2. I'm going down the 1 path, and then I print of n. All right, and I print n, and it ends up hitting this if statement and then returning. Right, so the next time around, it's actually never going to hit the debugger anymore. If I do, it's interesting. Oh, yeah, this isn't showing me what I want to show. What I essentially want to show is this. I'm going to show it.
Yeah, you can write out the tree, but I think it's like very useful just to think of it, because the tree is a little bit misleading in the sense that the order in which the computer executes.
Mm-hmm.
If you just think of that return Fibonacci n-1, you just expand it out, right? And when you're expanding it out, you're going to see that the computer executes those orders sequentially. And then when it does the plus Fibonacci n-2, it's also expanding it out. Does that make sense? So it's just like calling another function, but this time it's recursive, so it looks a little bit confusing. But just imagine like it's a different type of function in Fibonacci n-1. It's going to call that function first, and recursively keep calling that function first, and then it's doing the plus Fibonacci n-2 and expanding that one out. Does that make sense?
Okay. So I feel like my hypothesis about the first one, at least, was kind of correct, where like it is running the first function first, or like at least recurring down the first function first.
Yes, absolutely.
And then I guess I don't understand, do we not start from 4 in the second function? We do, right?
Yes, but when we return, so where does the call stack go? Right, so it starts at 4. We're like, we go through this, we hit this if statement, doesn't work. Then we go down to 3, right? We do n-1, and we're here, right?
Mm-hmm.
Then we go down 2. Then we go down to 1. Now where are we? We return a value, and we're at 2. Oh, we're finished here. We return a value, and then, well, actually, well, yeah. This goes to 0, sorry. All right. We return a value, and then we're, then we're, I was wrong to do it, right? So what, scratch that. Let's go 4, 3, 2, 1. We're down all the way at the bottom.
Okay.
No, it's a little bit confusing because, yes, you're calling the function on the left first, but remember, because you're recursively calling it, then there's 2 other new Fibonacci of the n-1, n-2, and then you're still, while you're traversing down the left Fibonacci, remember, each level, you're dealing with another 2 Fibonacci in the return. Does that make sense? Until you hit the base.
Yeah.
Does that make sense?
That. That's what the right-hand side of the tree is there?
So while you start with the left-hand side in the very first step, remember, in the second step, because you call the Fibonacci n-1, but Fibonacci n-1, if it's not the base case, is already 2 other Fibonacci pluses right there, right? The 2 other Fibonacci functions. but then you're still hitting the left and the left and the left. But remember, each level as you're going down the tree is also another Fibonacci n-2 that you have to take care of, and that all gets wrapped up. Yeah.
Yeah, Matt, this tree actually helps a lot to visualize it. That's really great.
Right. So you go down 4, 3, 2, 1, and I think the part you're missing is that after 1 you go back up to 2. Right.
Yeah,
So
that part is weird to me.
And then at 2, you just finished up this hand side of the equation, and then you still have to go down the right hand side of the equation.
Okay. And that's how you get 0 there.
Yeah, and then you go to 0. And this is actually the power of doing recursive problems, is you maintain where you are in this function. Right? Writing this function as without recursion is much trickier for this reason, especially if you're trying to solve it going down. Because it's very hard to keep track of where you are relative to that other value. Whereas if you have functions, as soon as you return to a function, you're just at where you called it. Right? And in that case, you just called Fibonacci n-1, and then you solved Fibonacci n-2. Right? And so that's why the next value is this 0, and that's why when you go up from 2, the next value is this 1 that comes from the 3. Then you go up, and now you go to 2, and you have the 2 next, and then you go left, and then you go right to 0.
So then, I guess my question after this then is that, we're returning to recursive functions, and then you're kind of like passing values back up the tree. Is the end Fibonacci, is the end like the correct value? Which of these numbers are we summing? Like all of them in the tree?
Yeah.
No. So what you sum is the 2 values below you. Right, so when you're at 2, when you're solving Fibonacci at 2, you go down to the 1 path and the 0 path, and then you sum them, and then what you got is the value of 2. So you took Fibonacci of 1 and Fibonacci of 0, which sums up. Which sums up to 1, and then you return this value.
Yeah.
Okay.
Right, so this value returns that. Okay, now what does 3 do? 3 takes that value that was returned, and then takes the Fibonacci of 1, right, which is 1, that was 1, so now 3 is going to return a value of 2, right? It returns a value of 2. Where does it return this value? It returns the value to this Fibonacci n-1 equation. This is the equation that got returned the corresponding 3's value, right? Then you get the corresponding 2's value, which we actually already solved down here, which was 1. Right, so the 4th Fibonacci number is going to be 2 plus 1, which is 3. And then it adds those 2 numbers, and it just returns 3.
Wait, I guess you lost me on the last step. So the Fibonacci of 4 is 3.
Yes, right, so the Fibonacci of 1, I'm going to put in parentheses what it should solve to, right? So Fibonacci of 1 should return 1, Fibonacci of 0 should return 0, right? Oh, my spacing is going to be off. Fibonacci of 2, as a result, is going to return 1. Right? Right? Okay. What about a 3 then? 3 is going to take the Fibonacci of 1, which is 1, and it's going to return 1 plus 1, which is now 2. All right, what's the Fibonacci?
Okay.
Yeah, this hurdle of recursion is like a super important one. But like it's like a really tough one, and like more than happy to spend the time, right? Right. So one of the things to think about is like, what happens with this 2 value while we're going down this path? Right. Well, this 2 value is just the result of this. Like we can go down this path, and the computer in memory can store this value up until we're back at the same corresponding level.
Gotcha.
Right, so we go down here. We return
so then
1.
the Fibonacci of 2 there is 1, and then the sum of 2 plus 1 is 3.
Yep. And as a result, we solve 3.
Oh shit! Oh my god.
It is not always the case though that this return statement, which is good for our which is good for our recursive step, is also going to correspond to our final solution. Sometimes what you'll do is you'll create a helper function that is your recursive function.
Gotcha. Yeah, I feel like I've done that kind of thing for like depth first search and anything to do with trees.
Yeah. I mean,
Oh, wow. That's pretty awesome, and I think anyone watching on YouTube just learned something new. It's really great.
all two people, me and Tom, all learned something new.
Yeah.
No, I think
we
there's
need
three.
to switch over to Twitch, man. They have like
I think we're doing it. We're
coding
doing it next
teams
week.
there. There's like I watch like live coders all the time there. There's like
Yep.
it might be just a way to get some publicity.
Absolutely, yeah. I think Twitch is better in terms of
It
like
is a bummer that you can only do one though. I think that's horrifying.
that's a bad part. Like you can just
Or if
stream
you
it.
guys want to go out on a limb, I think you were talking about Facebook. Microsoft just dropped out of the race, so we could do Facebook gaming and be like the only coders there.
Are you serious?
Yeah, Microsoft just shut down their streaming platform Mixer, and they're supposed to partner with Facebook in some way. I don't know the full details.
Interesting.
But right now, like, there's like no one on the Facebook streaming platform. So I know you guys had mentioned that. It might be worth trying just to see if.
Get a sponsorship from Facebook.
That would be
Yeah,
awesome.
like they need people so bad that maybe it's more realistic than Twitch.
Ooh.
I don't know.
I don't know who's like I think gamers are great people to learn coding, but I also like if you're trying to game. I don't know if you're trying to learn how to code. But then again, being on Facebook, I don't know if that's like the ideal people trying to like, like follow friends, and they're like, oh, someone's coding, let me learn this.
That's part of how we can advertise the game. It has a programmatic interface.
Oh
So
God, the game.
You can learn to code while you're gaming. That's gonna be huge.
Well, it's like my argument is that Twitch is the
Yeah.
same thing, but like if a coding community has grown there, like it should be able to grow in any streaming platform.
Yeah, I believe it. Do you want to go through Fibonacci 2 and Fibonacci 3? Do you know why they're different?
I'm good. I kind of like I get impressed with it. I can only handle
Wait,
stuff
wait,
like
wait.
recursion.
Wait, don't delete that. I think I'm getting a little bit mixed with my numbers, but isn't like the Fibonacci of like 3 plus 2? Isn't that like 5? There's no 4 in the Fibonacci series, unless I'm like.
No, 4 is the input, so the flip number is 3. The answer is in the parentheses.
Okay, it's 3. Got it. Okay, that makes sense. Yeah, I'm getting a little bit one-off indexing stuff. Okay. That makes sense.
Yeah, so the number in the parentheses is the answer. The
Yeah.
number before the parentheses is like what place we're looking at.
Yeah, I think just I really appreciate this just because my main confusion comes from like, all right, we're recurring. What the hell are we adding together? And at what point is Python like adding those values together? Like the answer is at every step, but I didn't fully understand how each iteration in kind of like the recursion tree feeds into the next one. Like you're returning a value, but what are you returning it to? You're returning it into the next like leaf in the tree kind of.
Well, I think it's like you should just really write out like, okay, so you see on line 7, return Fibonacci n-1 plus Fibonacci n-2. Just like literally write it out. So write out Fibonacci n-1, which is I think our input is 4. So just do Fibonacci 3 plus Fibonacci 2, and then inside Fibonacci 3, right, expand it out. So then Fibonacci 3 will turn into Fibonacci 2 plus Fibonacci 1, right? Plus Fibonacci 2 from before, right? And then you're just writing it, and you're just expanding it out. So there's no magic to it. You're just expanding out. That you still have the same return statement in line 7, but instead of, you're not really returning 2 functions. You're returning like many of these functions, but all expanded out, right? You're calling Fibonacci multiple times.
Mm-hmm.
Does that make sense?
No, it does make sense, and I do think I just need to spend some more time to do that. I think it's just like a constant journey of demystifying recursion for me, and it's one of those things that I I only really care about spending time on it when I'm like, trying to interview or something like that. To be perfectly honest.
Absolutely. No, I mean, so the irony of it is, like a lot of these like more computer science problems don't come up as frequently as the interviews make them seem.
I feel like this stuff is just kind of baked into most programming languages, and you don't think about it, like out of the box functions like min, max, things like that.
Yeah.
Oh, absolutely. Implementing min.
Yeah. No. Like this kind of problem, you can have a cache, but in terms of the efficiency, you want to write Fibonacci like iteratively. You want to have a for loop, and then you're just adding two predecessing variables, and then you just do it in a for loop. But like, it's fun because you can see like you're recomputing the Fibonacci like n-2 multiple times on both sides of the tree. So then that's when you bring in the memoization and the caching in, so you don't reduplicate those recursive calls, and that's basically dynamic programming in a nutshell.
Matt, is that legal? I don't think you can import like that.
Am I doing it backwards?
Yeah, you can do it backwards. It's TypeScript too much.
Yeah, there you go.
Yeah. All right, so what should I eat now? I need to order.
Oh man, I had Indian for lunch and I'm so full. I'm just skipping dinner altogether.
Do you guys have any coupon codes or anything?
Look at him.
I've been using an app called Chow Now instead of Seamless to order.
Chow Now. Nice.
Prices are cheaper, and apparently they don't like gouge the restaurants like Seamless do.
Well, they're not gouging. Well, maybe they're gouging the restaurants, but they're charging me if I get delivery for like a service fee of like 10% or 15%.
Yeah, it's super expensive. That's
what Seamless. Yeah, I mean,
Uber
I
Eats,
just found
everything.
that this app, the prices are cheaper, and they don't do that bullshit.
Chow Now. That's interesting. Hey,
No,
Chow Now should sponsor a
There
channel.
are fewer restaurants though.
Yeah, I don't order delivery. I always pick up my food. I'm trying to
No,
save
me
on
too.
money.
Yeah, it's so expensive.
No, same here. Even for
Sounds
pickup,
like you guys
like,
hate the
mobile
local
pickup.
economy, is what I'm gathering from this conversation. So you guys aren't proud patriots.
Wait, what?
I'm just messing with you. I'm making a joke about like you guys not being proud patriots for not wanting to spend money on other people.
Oh, I love capitalism. Huzzah! Seamless, take my money. Probably doing amazing right now. They don't need more money.
But the delivery guys, I'm sure they fucking do. Actually,
Yeah.
no, delivery guys, no, the restaurants are the ones.
There was a
No,
whole
wait,
scandal with the tips with Seamless, though, that the delivery guys don't actually get the tips.
Are you serious?
Or, I'm not sure if it was Seamless or Grubhub, which I think owns Seamless.
It's the
or
same.
It might have been DoorDash. I don't know. I don't
Oh,
trust
it's
any of
DoorDash.
these
Yeah.
companies. It was DoorDash?
Yeah, they got into a really big trouble.
Yeah, because it's super shitty.
I know. Hey, stand for NBA, man.
Alright,
Okay.
sorry to tarnish the live stream with talk of Seamless and DoorDash.
Yeah, that looks like we're getting that endorsement from them, huh?
Oh,
We're getting
You're absolutely right. We'll have to burn this video.
How many bridges can we burn? Is the question in this
Well, Chow Now might sponsor us.
Exactly. Oh, actually, I'm gonna put a hashtag here. Chow Now, sponsor us.
Oh man.
Chow Now.
All right. This turned out to be. We had a small group today, but I think this turned out to be a really good episode.
Yes, absolutely.
What happened for the first hour and a half?
Been nonstop dynamic programming.
Yeah, it truly has been. Oh, yo, Matt. Also, I want to show you. You know, you can enter like a README viewer mode in VS Code. If you like have your README file open, you can press Alt Shift V, and it will turn it into like a literal README on like GitHub or something. It'll render the markdown.
Oh, yes. There's actually an extension for that as well.
I don't think there needs to be though.
No, like he automatically opens a side window with the actual how it's going to look like. So
Yeah, so I've seen that, but I don't like it too much. You said
Wait,
Alt
wait.
Shift V? Is
Click
it
on
Option
the
Shift V?
document. Click
Yeah,
on the
I'm on it.
document. Oh, I don't know. It's Alt Shift V on my PC. Maybe it should be Option Shift V then.
It should be.
Yeah. Let me double check.
Well, I got a discount for Five Guys. I'm gonna get Five Guys.
Five Guys is good.
I'm only getting them because I'm getting a discount.
Yeah, open preview and markdown. This is it.
Oh, sorry, it's Command Shift V then. My bad.
And Shift V.
Command Shift V should do.
Oh
it.
yeah.
There you go.
But oh.
Oh, so you don't have to install anything.
No, wait. What's going on? Like, is it this? Is just automatic Markdown?
Yeah.
Wasn't this already? Wasn't your README already in Markdown though?
It's not rendered markdown. I don't know. Here's the thing though. I look at this all the time. So like.
No,
this is
you
more
can click
comfortable to me.
No, you can click preview on the top right. Just click on the pane on the top right in VS Code. Yeah, just click on the middle button on the top right. Yeah, click on that. Yeah, that's already been a function. That's already you can do this for every Markdown file in VS Code.
Dude, I absolutely reject not using the keyboard shortcut. I reject that.
Me too.
No,
Me too.
God.
that's the gamer in you. You have to find.
Ever since you had to leave in. No, but here's the thing. I'm so used to like regular like the actual markdown syntax, like actually seeing hashtag that like going into the other one just looks foreign to me.
No, just click on the preview, then you can see it side by side. That's what I do. I mean,
But like I never look at like actual markdown. You know what I mean? That's my point.
Yeah, he just look at the actual codes.
I just always look at a Ruby.md.
I'm a master in Microsoft Word.
Oh no, Google Docs is better.
What's better?
Google
I used
Docs.
to be super good at Excel. I'm pretty bad at it now.
Solve a dynamic programming problem in Excel.
That was bold of you, to be honest. Even if I had that thought, I probably wouldn't have put in the time and effort to do that. Good for you, man. It is like seriously
It
a
wasn't
good
hard
learning
though.
tool.
Is the thing though, because like literally that like extra hurdle where I was saying like between on step 2 is the hurdle. As soon as you figure out that equation, all it is just copy and pasting into every other cell. Right?
See, but I understand that, but that was actually one of the problems I had with the example was that I started to kind of see the pattern in Excel, and it was almost like I had to stop my brain from being like, oh, I get the pattern, so I understand the problem. You know, because like it's like, oh, it's just the Excel function. It's like this shape, kind of, you know.
Yeah.
So when you deleted all the rows, it was extremely helpful for me for that fact. That I was like, okay, I don't really see the pattern in the numbers or in the functions themselves.
Good.
No, but the visual part is very important. Like it makes you understand like completely on a different angle. Like it makes it so much easier.
I also think especially students who are more likely to be coming from an Excel background into like a bootcamp kind of thing would be more receptive to that.
So the other thing to note is let me go back to sharing this. You can actually like, this is also a map of the recursion or even like a recursive solution and what the input is, right? So the input, the rod length is 5, and then if you're trying price 2, this is that solution, right? So like, it's important to know like these numbers are also going to exist in your Python script, and kind of mapping where they are in this Excel sheet to where they are in the Python script will be super helpful.
Gotcha.
Okay, what's next, guys?
Five Guys.
Alright, man.
And I'm about done. You guys want to shoot the shit, I'm down, but I'm not coding anymore.
No, I'm probably taking a break. I got plenty more coding to do tomorrow.
Yeah, me too. I gotta work actually.
It's time for video games. That's what you guys are saying.
Oh man,
I wish.
I can't even find a video game I'm into lately. It's so annoying. I was playing the Borderlands because I got that for free from Epic, but even that I'm just like, man, this is kind of okay. It's a little clunky.
What kind of games do you like?
Dude, it's such a hard question. I don't know. I thought I used to love like single player story driven games, but then I
What's
even
your
fell
favorite
off
video
those.
game?
Wow, that's
Hard.
easy. WoW is epic. You're
More
WoW.
recently, like no, I quit WoW.
Yeah.
And I wouldn't play WoW by myself. Also, like I had friends I was playing with. It would be not as fun by myself. But more recently, like Zelda Breath of the Wild is definitely like
Nice.
like
That was a
the
good one.
game. You know, I just actually feel like it ruined like so many other video games for me. Like maybe it was also just like getting the Switch at launch and playing the game that like doubly made it amazing.
Have you beat it since the expansions came out?
I didn't buy the pack to get the expansions, actually.
Yeah. So
At
I
that
actually,
point, yeah.
I beat it like way before the expansions came out, and like I tried playing a little bit with those, but like honestly, I don't know. I wasn't into it by that point.
Yeah, it felt like a complete like experience to me, and I didn't really want to go back per se. I'm not like a completionist when it comes to games or anything like that.
No, I usually am, and that was kind of the first game where I was like, no, let's just go through things.
What? Really? So surprised.
You guys don't play PlayStation 4?
No.
I have a PC.
No, I have one, but it's still. I got it from this recruiter, and I still haven't opened it yet.
What do you mean you got it from a recruiter? What?
I got it from my recruiter, and then it's like I still haven't opened it yet. It's still fresh in the box, like brand new condition. Has not been opened. The
Sell
box
it.
is still there.
Are we still streaming, or are we
great
done?
games.
I mean, like the thing, I don't even have a TV, so it's like I don't know what to do with it. It's just sitting, just gathering.
Just sell it.
dust.
Plug it into your monitor, dude. What? PlayStation has amazing games that aren't on PC. It's freaking
But no,
nuts,
but then you have to
actually.
buy the, you have to buy the games, and I'm like, I make games, I don't play games. It's
I
different.
don't know. Yeah, I know they give them out with like PS Plus or whatever sometimes, but you're right.
Tom, are we still streaming?
Yep.
You should
All
have.
right, let's close that out. All right, thank you everyone for following the stream. Have a good night.
All right, guys, have a good one.
Appropriate.
Bye, Ari.
All right. Bye, Ari. Oh, somebody just came and watch. No.
All right,
All right.
so
Bye, guys.
I'm gonna stick around. I just want them to stream.
No.
Just say goodbye. Oh man.
Yeah, I mean, I want to shoot the shit. I don't want to do it like when I'm worried about saying something stupid, you know?
No, yeah, I know what you mean exactly. It's easy to forget as well.
yeah, I'm not getting Five Guys. It's too unhealthy.
Dude, what the hell? You just said you had a coupon.
Yeah, it's only 10% off. It's not worth it.
You're actually making me hungry now. That might really eat my food. But it's 9 o'clock. Like, I just, it's time to freaking wind down. Have some chamomile tea.
Well, the problem is the restaurants are still they're still operating under like somewhat limited schedules. They're not open till like 11 anymore. Then now they close down at like 9 o'clock. So that's a little bit. So I should be ordering now.
Oh, yeah. You're absolutely right, man. At least places are open a little later. They're not closing at 8 anymore.
Yeah, for a few places, but like I'm not sure if Dos Toros was ever open like past 8 before, but now they close like at 8 around where I live, and I eat like Dos Toros like every other day.
Oh, yeah. Do you eat those tours every other day? What the hell?
Yeah.
Good, man.
Edwin, there is
I do like their quesadillas, but man.
No, the burrito is pretty healthy. It's like 1,000 calories. Pretty good. It's good sustenance.
Burritos just knock me out. I can't eat them. Like, I even have like a healthy in quotes, Mexican kitchen near me, and like those burritos absolutely knock me out.
Oh my god, I need to get food.
Dude, just cook at this point. What the heck?
Yeah, but I already cooked this morning. I mean, damn, it sucks. Oh.
I don't. once a day. Good for you.
Wait, you cook like twice a day, or like microwave?
I usually don't. I've been really consistent about not ordering out. I don't microwave. There was a microwave here when I moved in, but I put it in storage.
Edwin,
Like,
he's
8
Italian.
microwaves.
He's Italian. He cannot
Oh,
use a
yeah.
microwave.
I got groceries like crazy, man. I got fresh pasta in here.
Oh my god, I guess I have to cook. Oh my god.
Oh, actually, talking about food, I went to a restaurant today with Z to have
Okay.
lunch with her.
Wow, that's awesome.
Yeah.
So I guess you're officially not social distance anymore.
No, because they opened the patios now. I mean, I haven't been out in so long. Like, so weird. Actually, yeah.
Yeah. My block is absolutely popping, dude. The restaurants just have like these tents in the street and like everyone's hanging out super close. It's just how it is.
That's dangerous.
Oh no, I think I'm getting $5 off from Seamless. Okay, now it's time for some good Asian food.
Dude, but they tell you $5 off, but Seamless bakes it into the prices.
I know, but it's like, fuck.
Just get chow now. It's better. Chow now. Let's see. Chow now.
Oh my god, that's nasty. How can they do that? That's like some marketing trick. That's nasty.
Yo, Matt, I'm really looking forward to your live code on Sunday. I'm inspired. I want to do some live coding.
Oh, so
Come up with a problem too.
wait.
I mean, like literally, what I want this to do is make it as easy for any of us to do any of these things.
But like, isn't it super easy anyway? Like, you know, like Discord's doing it. It's really easy to stream on Twitch if you have like
No, to
NVIDIA
do it, but,
whatever
like,
on your computer.
Tom and I are like Saturday. We're also gonna I'm gonna be at Discord as well, so like people can hop in and actually not just watch, but also like help out.
Sure.
So
if you're like just learning JavaScript, perfect. Like I could use you to do the work for me, and I'll just help you explaining all the stuff that you need to do. You know?
It'll take you 2 years to write your web app, but yeah.
Well, no, seriously. Well, like, yeah. I mean, it would definitely take longer, and it definitely take a lot more explaining. But like Tom and I were talking about this, and Tom's like, "What do you want to call this thing?" And like, honestly, what I was thinking about is like, calling this this thing like "do my work." You know, like making a joke that like I'm gonna get junior people to do my work, and I'm just gonna publicize it, and I'm gonna help them out along the way. They're gonna learn because I'm gonna like be very informative. But like, fuck that. Let's get you to do my work.
no, but with all honesty, I mean that as much as this sounds fucked up, I think that's the best way to learn. No, seriously.
No, it is absolutely the best way to learn. Where else do you get like a senior engineer to coach you into making a web app? Exactly
my point. I mean, and like, if you're complaining that you got a work to do, so you're not fit to be a software engineer. You know, like really, like you want to do work like learn shit, not doing anything. Like I'm sorry, but there's no such a thing. Like
classic. Ugh.
I'm getting this pizza.
Oh no, it's pizza.
Nice.
Very healthy.
Now I make you jealous of it. I'm getting this pizza. Nothing else is open. That's the problem. Only like pizza places.
What?
Just
Times Squares is closing. What?
Just download Uber Eats.
No, I'm using Seamless because I'm getting this $5 off coupon. But let me see if Uber Eats is giving me a coupon.
Edwin, what do you think of the market these days?
Bless you.
Well, thank you.
Market? The
Which
one that's acting all retarded.
Huh?
The one that's acting all retarded.
What market? Like the financial markets?
Yeah.
Oh, I haven't checked that since I quit my job like last year. I haven't even checked the markets. Well, I did check it when the prices were going down like a few months ago when the market was crashing all the way down to like 2000. And then I checked my like 401k and I was like, holy shit! Like I had no gains at all. But I think it's a lot better now, right? I didn't sell anything, but it's like, fuck. That was like, it doesn't matter. Like I think buying and holding is the right thing to do, but But it could like you could be saving up for like 5 or 10 years, and then in like a period of a few months, your entire like retirement savings can all just go down to the tubes. It's pretty incredible. So, but that's my thought of the market.
Classic.
Yeah, I haven't thought about. I haven't been. A lot of my friends are using Robinhood, and apparently, like all over the news, like Robinhood and all these day trading is becoming like a big resurgence of that, like of Wall Street bets.
I mean, like everyone's
Wall Street
bored.
Yeah, like my friends are just like on Wall Street bets and like just trading Robinhood, and they seem to be making a lot of money. But I think it's a very crazy market right now in terms of all the enthusiasm. But like I would not touch it. Like I have nothing invested besides my retirement stock index funds.
Yeah.
Are you holding cash?
Like yeah, well, I'm probably not the best person because I've been holding cash for like the past like I thought there was going to be a recession like 3 years ago.
Right.
Like so I'm probably not the so like I've been holding cash for like the past few years, and I probably lost a lot of gains, but the thing is sleeping well at night. I think that's the most important thing.
Yeah, absolutely.
That's,
Yeah.
I
This is inflation.
haven't
I mean,
been
the cost
as
is useless.
stressed as like since trying to actively trade stocks is just like terrible. Like just now.
Yeah, like well, I would just buy like a Vanguard. Like I use Vanguard, and I just I don't play with options or with. I just buy index funds and for my retirement, and that's it. I'm not playing with stocks. Yeah, but yeah, that's my financial advice.
No, that's good advice. I
Yeah,
don't think you should hold cash though. But I get the feeling of like anticipating a recession.
Yeah.
But I think like Vanguard has a very good study on like timing the market versus versus putting money incrementally into the market. That shows money incrementally into the market outperforms in like 70-80% of scenarios. Like regularly putting money in.
yeah, definitely.
But like
Yeah.
putting money into the market in what way? Like just big ETFs.
Yeah, ETFs.
And
ETFs
not
is
just
really-
not just any ETF. Like I because I'm pretty diversified. I've invested in like developed economy equities and like emerging economy equities. None of them have done as well as the U.S. stock market. So I think like just like general advice is to invest the most of your money in just like the U.S. stock market. I think that's like a good idea because like diversification is good, but all the other markets are just not doing as well for some reason over the past like 5 years. But and I think I think America like I think it's basically like what Warren Buffett recommends, right? He's like just invest in America and you'll never go wrong. Just buy some like U.S. stock ETF and then you'll never go wrong with that.
and proceed to hold in cash, man. That's like yeah, Warren Buffett is one thing, but he's not really doing it.
Well, no, but that's his advice for people who are not actively choosing stocks, right? You just buy a U.S. stock ETF and just hold it forever.
I mean, that's general advice. That's like good advice across the board.
Yeah.
You will likely do worse not doing that.
But yeah, no, like I've given up on that life. Now it's all about video games. That's my life now.
Oh, actually, Lee was here for a quick second and he left. And where is he?
And for you, for a second too.
Yep. They were like, "Where is Edwin talking about video games?" You're like,
For real?
"No, I'm just joking," but you know.
No, video games forever, yes. Not playing them, just making them. Like, have you guys ever watched Scarface? Don't get high on your own supply.
Oh,
man.
oh, can I make an announcement since we're streaming, Edwin?
Wait, we're streaming?
Yeah. Do you mind donating that PlayStation for our? So we have 14 subscriber. Maybe when we get to 50.
Wait, what?
to
The subscribers, the PlayStation is actually a computer that will count as a subscriber.
The giveaway.
You know, it's a giveaway. Sometimes YouTubers they do that to.
Oh,
Yeah, we're not. That's like a $500 thing for like. I don't know if it's a like big.
Yeah.
I don't know if we've made like even $1 at that point. You know, like let's wait until we made some money before we're giving things
No, that's
away.
why I'm asking for a donation from Edwin.
No, I think putting it on Twitch and having a higher resolution video, I think they'll get more viewers.
Is the resolution that bad?
The resolution is pretty bad when I checked it like last time.
Maybe it's your internet, no?
No, it's the recording of recording of a Discord video is just not that good. Maybe even the Twitch streaming is not that good. I think.
No, Twitch is
there's
good.
A way of like
Twitch is
making
good.
it better.
Twitch
yeah,
is.
but I think the act of recording a Discord streaming, it just doesn't look good. It looks like you're recording a recording. Which,
I mean, like, streamers literally buy entire PCs dedicated to streaming their other PC.
Exactly. Yeah, you're absolutely right.
So maybe we can use Edwin's PlayStation for that.
The PlayStation only has like 30. The PlayStation is pretty bad, right? It only has like 30 FPS, right? It's pretty bad.
Yeah.
Like console games are just terrible. Like it's all about the PC master race.
No, like when Xbox was coming out, they were like 60 FPS. You wouldn't believe it. And, like, anyone with a PC is like, yeah, 144. Like, what you gonna do? All right. I think that's it for me though. I'm gonna start winding down, watching some Netflix.
Oh wow. All right, yeah, I'm gonna have to get some food. Well, I'll talk to you guys later.
This
All right.
like hour before bed is critical, man. You gotta like just chill out.
Definitely.
Just don't touch the WoW.
I quit. Wow, what the hell?
And then it's gonna be like a week from now. Sorry guys, I'm in a raid. That's
Dude,
literally
not anymore. That shit is so stressful. I don't even want to do that anymore. It was the least fun part of the game. Fucking ridiculous. Can you imagine trying to organize 40 people over Discord to not like like to coordinate them? You can't even do that in like real life. It's ridiculous.
Well, that's pretty wild because like I thought WoW was like dead, but apparently it's still very active.
I think
So-
people just really